Okay, so this morning I thought we should talk about seismology. So that's one topic only. Oop. So seismology in general, but neutron star seismology in particular. And so what I'm going to do, I'm going to talk about four different kinds of oscillations of neutron stars. I'm going to go through one of them in detail, because it's easy enough that I can do it. And then this afternoon, I'm going to ask you to fill in some blanks in that calculation and compare to if you do it a little bit better than what I'm going to do it. And then we're going to look at some other kinds. The first one, basically the idea is, I'm going to do a very, very simplest case on the board. And then I'm going to put in a little bit more physics and ask what happens, how does this problem change? And then I'm going to put in a little bit of different physics, namely rotation, and I'm going to ask how does the problem change now? Okay? And what you're going to see is that you start out with a simple fluid sphere, and you start and you ask, how does this sphere react if I kick it? It starts wobbling and oscillating just like a string, essentially, in its different modes. And the more physics you add to the star, the more different classes of modes do you get. Okay? And the story, as we often tell it, is that each kind of mode is associated with one piece of physics. So I'm going to start looking at something called the fundamental mode. It's there essentially because it's sphere, okay, and has a surface. And then we're going to look at pressure modes, which are there because the star is not uniform density. If you push it, it wants to restore itself by pressure. It has sound waves. And then we look at something called gravity modes, which are there because if you take a fluid element to some depth in the star and you move it, it might not want to be in this new location because it might have the wrong composition, the wrong temperature or something like that. And there may be forces that push it back. If you push them back, then it can oscillate back and forth, and that's called the gravity mode. Or these guys could be unstable, so this guy just keeps on going, and then you get something called convection. Right? So these are quite simple to understand. And then we're going to look at R modes in a rotating star, just as a sketch, to illustrate what happens when you add rotation. So these are just examples. But this simple story, you should just know from the very beginning, in reality is more complicated. These guys mix up and they're not so clean, and so the real calculations are much, much harder than we're going to do today. But still, if we don't understand these first steps, then there's no point in trying to do these harder calculations. Okay? But let's start from the beginning. Why do we think this is a sensible attitude, and what do we hope to get out of it? Well, for neutron stars, to do seismology is kind of a dream. We're not there yet. But for normal stars, say the sun, this is technology that's being used all the time. So in the case of the sun, it's called helioseismology. People use observations of the sun's surface or variations in solar wind, etc., to figure out that the sun has many different oscillations. And they use the observations paired to calculations like the ones we're going to do, but a little bit more advanced, to figure out, for example, how the sun rotates not uniformly, but slightly differently. So you can figure out what the local rotation velocity is at different depths by combining this seismology information. Okay? So that's something we wouldn't know. And the idea then is we're probing what's happening on the inside by looking at these signals. Okay? So that's the attitude that we'd like to adopt. Okay? For general stars, astroseismology, this is also a big program now, and it's closely linked to the search for exoplanets, which is, in astronomy, one of the big areas now. Okay? But what we want to do for neutron stars is we want to do the same kind of thing. So we want to be able to use observations of any kind. Of course, this week we would like to use gravitational waves, right? Ultimately, to probe what goes on in the interior, to learn something about the physics, the equation of state, maybe composition, and so on, okay? And what we're going to see today and tomorrow is that this is a very complex program, but really it does involve a lot of the physics that people that build equations of state and so on worry about. So it has promise, but obviously it's going to be very challenging. Having said that, and we're certainly not there with gravitational waves, that's for sure, but we're beginning to have opportunities to realize these calculations and test them against observations in X-rays. Okay? So maybe something like 10 years ago, there was a discovery that in the tails of giant flares from strongly magnetized neutron stars, magnetars, you could see quasi-periodic oscillations. Okay? And the idea was that these flares originated from the crust of the neutron star breaking. So the magnetic field evolved, stretched the crust, it broke, it started oscillating in different modes. So we had an opportunity to compare our calculations of modes in the neutron star crust, which I won't be talking about because they won't be radiating much gravitational waves. But anyway, we could compare those calculations to the observations to find that actually this explanation kind of works. Okay? But then, as I told you yesterday, the answer in astrophysics is always the magnetic field. So what we learned from this exercise, that this pure idea of crust oscillations is not so clean, because if the crust moves, it will wiggle the magnetic field, and that will communicate through the star's fluid core, and so this pure crust explanation is not clean enough. So now we had the problem. We had the problem that the crust oscillations explain the data, but that calculation could not possibly be right. So people have spent the next years, nearly a decade, trying to understand why it is that the magnetic field is important, but yet totally unimportant. So to try to put the magnetic field into this calculation, but make sure it has no effect. And that's really difficult. Okay? So this problem and that problem has become confusing. And I stopped working on it almost 10 years ago, I think, having done some of the early work. I stopped working on it because we had this set of notes. It was growing, handwritten notes. It was a stack like this, I think. And they didn't lead anywhere. And I just said, this problem is too confusing for me. I just have to stop. Other people were brave. They carried on to do proper simulations and things like that. And it's still a little bit confusing. But it tells you a little bit how these things go. The other thing that's very exciting, I think, but unexplained, is that in two of these low mass X-ray binaries that we talked about yesterday, that you worked out some estimates for, we have seen, in addition to the effects of the rotation, the pulsations linked to the rotation period, we've seen one other frequency. And so the question is, what frequency? So there's been some speculation that it has to be a mode of the star in some shape or form, perhaps some feature in the star's very thin fluid ocean that influences the X-rays. It could even be one of these modes we're talking about today, the one at the end, the R mode, but there are some problems associated with that interpretation. In principle, it fits if you just look at the frequency, but it doesn't fit when you start asking what else would happen to this star. So the story is, we're beginning to do this for neutron stars. The problem at the moment is that we used to do these kinds of things with mainly X-ray data from the Rossi X-ray Timing Explorer, which sadly went out of operation a few years ago, and now we're in the era of AstroSat, which is the only X-ray timing experiment we have, right? It's very, very important, which is an Indian mission. And we're hoping, we had proposed to the EU something called the LOFT twice, and it did not go through. It was a fantastic mission, and that has now morphed into a ESA Chinese Space Academy program called EXTP. And then there's a new loft in the US proposed NASA. So these kind of missions might be coming, and they're very important if we're going to do this kind of thing, because ultimately, and obviously with gravitational waves, as I'm going to tell you today, we'd like to do this too, but we need the complementarity between the two. That's very, very important. Okay, so I'm going to talk about how this goes. And the first thing I want to do is I want to work out, for reasons that will be clear perhaps, I want to work out the fundamental mode of a uniform density, so not a real star, I'm just making density constant for simplicity, okay? Non-rotating fluid body, okay? So that's my first thing. And what I hope to get out of this is a couple of things. I hope to get out of this the general setup. You know, what are the ingredients that always go into this calculation? I hope to get out of this some kind of scaling at the end. What is the frequency of this guy? And how does it depend on things like mass and radius? And then I can start asking, what happens if I put in real equations of state and I change this? What do I think will happen? Okay? That's what I hope to get out of doing this. Okay? So the first thing we need is fluid dynamics. And because we would not be able to do this in general relativity, we're going to do it in Newtonian. And so as we concluded, or we could have concluded in the first tutorial, if I'd set up the problem in a doable fashion, of course I didn't, we have the two equations in Newtonian for a non-rotating star. We've got the continuity equation for mass conservation, which simply says that the time derivative of the density is the divergence of the flux, like this. And then we have the Euler equation, which says that the time derivative of the velocity convective derivative 1 over the density gradient, that should be upstairs now, of P plus gradient of gravitational potential is 0. Okay? So that's always the starting point. Oh, and then we have the Poisson equation for the gravitational potential. So that's essentially the problem. But now, what I want to do is I want to ask, what happens if I kick this object, but I take a background star, if you like, which in some sense is my equilibrium, which has no velocity, just sitting there, and it has uniform density. So there is obviously no, there's an incompressible object. There is no such thing in reality. Water is almost incompressible. Neutron star matter is definitely not. Okay, but this simplifies life, as you will see in a second, quite a lot. Okay, and then we kick this. And now you have two choices. You can either perturb a fluid at a fixed location. So I pick a point in the star and I say, how does H quantity vary at this point? It's called an Eulerian perturbation. So in that case, for example, for the pressure, you say that the perturbation in the pressure is simply the difference of the pressure at the position x and time minus the original background one at the same position and the same time. This doesn't depend on time, but it's like this, okay? Sit at this point and you just compare what's the value now compared to the value in equilibrium, okay? So that's option number one. Option number two is that you move along with the fluid. You pick a fluid element because you like it so much. And then you go with it wherever it goes. You say, how does things change when I move around like this? Okay, now you see the difference is you need to keep track of where you are, okay? And then you define a different perturbation. I'm going to write this delta p like this with an uppercase delta, which is the same as this first guy, but has an extra bit, okay? And that extra bit is just the vector that connects the original point with the current point, and then what the background, this P naught, essentially was, right? So now you can see that if I have variations here, I pick up a difference between these two. So today I'm not going to be using this much, apart from I will need it in a couple of times, okay? I will need it when I talk about what happens at the surface of the star, right? Because at the surface of the star, it's not so easy to say in this description what's going on, because if I say, oh, this X is at the surface in the beginning, but as the star oscillates back and forth, that's not going to be the surface, right? So in order to define the surface, I need to see the surface and ride along with it, and that means I have to do it this way, okay? I'm going to spend quite a lot of time tomorrow in this picture, because when you start talking about rotating stars, that's the natural thing to do it, natural way to do it, okay? But today, I'm going to try to do it this way, because this is a little bit easier, okay? And if you want to do this on proper, the reason I want to spend time on this tomorrow is that, first of all, it's a natural way to do rotating stars. It will tell us something very important about stability, which is going to be the theme for tomorrow. But also, if you want to do relativistic perturbations, that's also a very natural way to do it, okay? But that's not for this morning. Okay, let's ask now what happens then. I want to perturb this guy. So let's see what happens to the two equations. First of all, the continuity equation. I have said that this density is absolutely constant, right? So when I perturb this, it doesn't have any perturbation, so this has to drop out, okay? The density is constant, so I can take this outside the derivative, right? That leaves me just with the divergence of the velocity field, and then I perturb this, and if I do it this way, then this is at a fixed location, which means that the perturbation and the derivatives commute, okay? That's not true for the Lagrangian one, and we're going to have a look at that tomorrow, okay? But in this case, they commute. So the first one, I just get delta VI, right? So now you see why I wanted to choose that constant density, because that just collapsed this into a very simple thing, right? The second thing we have then is the Euler equation. Now we get a time derivative of the perturbed velocity, and then we perturb this quadratic guy, the part of the convective derivative, but I get then a perturbation times the derivative of the velocity, but the velocity was 0 in background, so that goes, and then I get the background times the, so this term disappears, okay? And then I get here, but this density was constant, so that doesn't do anything for me. The only thing I get is, again, commute this, get a delta p, and over here a delta phi. Okay, so that's also much easier. So then I get a dt delta vi plus 1 over rho grad delta p plus grad I delta phi. And finally, another nice outcome of what I did, but will be trouble for you this afternoon. Okay, you don't like me saying that now, because you'll worry all the time until the moment hits you, okay? I perturb this. Again, this is a spatial derivative. That perturbation goes straight through, but this guy is constant, so that vanishes, okay? Okay, so here's the problem with those assumptions. So one thing that's going to cause a mess for you this afternoon is the fact that this assumption of constant density, when I do this perturbation trick, is problematic when you want to match the interior to the exterior. Because in this star now, I have a step in the density at the surface. And that step will, in some sense, give you a delta function later at the surface. So when you start talking about matching for the perturbed gravitational potential, you need to pick up that step. So for the exercise this afternoon, I've sort of explained how that is done, and you can just put that in. But for this morning, I'm going to skip it, okay? So at some point in a minute, I'm just going to throw away the gravitational potential altogether, okay? Okay, so now we have one more thing. Let's add the fact that this guy is irrotational. That means that we can write the velocity field, perturbed velocity, as the gradient of a scalar. Let's call it chi. Okay? Now if you take the curl of this, then that vanishes. So this is irrotational. So that's another assumption I'm putting in here, okay? But for an incompressible fluid, that has to be the case. Okay, now let's see what happens, and we can read off several things from here. First of all, you see that if I make this assumption here, then I've got gradients all over, and this guy is a constant, so I can pull that inside that derivative. Okay? That means this is a total gradient of something, which means I can integrate. Right? So what do we get then? We get a time derivative of this chi that I invented. We get 1 over rho delta p and delta phi, and all of that has to be some constant. Let's call it d. But actually, if I look a little bit closer and I make some assumptions about what has to happen, you can convince yourself that this has to vanish because it has to vanish at the surface of the star. Okay? So I can drop this d. I'm not going to go into exactly why that is true, you just have to take it on faith for now. Okay? And I wasted a bit of space here that I would need over here. I'll try to squeeze it in anyway, because it's not, the next step is not that big. Now let's have a look at what we've got. We've got this equation instead of this one. Right? We know that this one satisfies Laplace's equation. So if we took another derivative up here, right, then we get the Laplace piece here, right? So that would drop out. Okay? Now, moreover, we know that the perturbed velocity, or the chi, satisfies Laplace's equation. Because if you put this in here, that gives you Laplace's equation for chi. All right? With me? Okay, now let's see what we've got. I take the divergence of this here, that's 0. That drops out. This is constant. So P, delta P satisfies Laplace's equation. I have reduced the whole problem to solving Laplace's equation with these assumptions. Okay? That's why when you make these simplifying approximations, that's the trick. Okay? If you don't make these assumptions, you need to solve something else which is more complicated. But now, basically here, the upshot is so this is not how stellar perturbation theory goes. As I said, you have real equations of state or anything. But in this very particular case, it works. Okay? And so now, what we need to do is we need to go back to textbook mathematical physics. Okay? And actually, I have to do a little bit of textbook that students of today, at least British students of today, never do, to my great shock and horror, namely special functions. Okay? In a sense, what we need to do is we need to solve Laplace's equation in some coordinates, because we're dealing with a star, the natural choice is spherical coordinates. Right? It's a ball after all. And so the natural way to do it is to say that we have an x, function of r, theta, and phi, which is simply a sum over some xl and m, I guess, but let's just xl. Spherical harmonics. So the spherical harmonics are a complete basis of functions that satisfy essentially the angular part to here, built out of Legendre. How many people are familiar with spherical harmonics? There you go. See, that's the difference between Indian students and British students. If I ask my British students that question, they say, the what? The what did you say? And I say, oh, Legendre function. I said, the what? Oh, and then you write down the equation, the solution to this. I said, no, there's no solution to that. I said, but I can solve it. I said, no, you can't. And then you try to explain that special functions are really just names given to solutions to equations where you can't be bothered to figure out what the solution really is. But it comes up so often that you need to give it a name, because otherwise, you know. And then you go, what? And you say, have you heard of this? And they say, no. And you're stuck. So we have to stop now, and this is the end of the, for the British students, this is the end of the lecture. When that insult goes viral on YouTube, then I'm in trouble. Okay? But the bottom line is, if we just get rid of the angular, what we're left with now is an equation for the radial piece. It's a second order ODE for that XL. We've got a radial derivative minus these L plus 1, which you pick up from the angular derivative of this guy. Okay. And this you solve with the power law. So you just find that this has to go like A, R to the L plus some B, R to the minus L minus 1. This is all standard. Right? And you've probably all seen this before. Now, in our case, we know that B has to vanish, because otherwise we'll be dealing with some X that blows up at the origin. And that would be problematic, because that X is either delta P, delta phi, or this velocity potential, and so this would be a problem. So that B has to go. Okay? And now we're very near to the end. Now we know that each of our functions has to look like this, right? So we just say, okay, I know this. I know now that chi has some radial component, let's call it chi L, or all of chi, is something that just looks like for each harmonic has some coefficient AL and then a YLM. So I'm just assuming now that I don't need to sum, and as it turns out, I don't in this case, they all decouple. I have the delta phi. You will not be surprised that the coefficient is called little b. Very logical. Exactly the same. And delta p, again the same with the coefficient c. Okay. And now we go back over here. Okay. We assume that either we do a Laplace Fourier transform, or we just assume that there is a harmonic time dependent because we're looking for oscillations, so that makes sense, right? And that means that the time derivative here becomes an I omega times that exponential. And then we know that this is now I omega A coefficient times this common factor for all of them. So drop the common factor, it's irrelevant to us. And we just get a very simple equation that says I omega A plus the C for the pressure over rho plus the B. All of that has to vanish. So I've reduced, by using the spherical harmonics, the whole problem to algebra, right? Which is nice. But to finish, I need some relationship between these A's and B's and C's. And they're going to come from the surface. Okay? So now, for the purposes of this morning, I'm going to be really lazy, okay? I'm going to introduce something called the Cowling approximation. And that is, in this case, just saying that the perturbed gravitational potential vanishes. Okay? And obviously, by implication, that says that whatever this B is, I just drop it. Okay? Now, this is very common in studying all sorts of problems. These two words, Cowling approximation. Okay? But it's very problematic, okay? And in fact, for the calculation I'm doing now, it is not valid, okay? And one of the things we're going to be doing this afternoon is to show how not valid it is. Because I'm going to ask you to repeat this thing I'm doing now, essentially, just to firm it up, and then add in that potential, add the results. And what I think you're going to find, now we had problems with numbers yesterday, you guys don't know, but we got deformations of neutron stars that varied from 10 to the minus 20 to 10 to the 8. So we were doing good on the numbers, okay? And we even had Mathematica produce 2 different answers, so it was going well. Okay. But maybe if this works out this afternoon, you're going to find that for the most important, the quadruple F mode, this approximation I'm doing now is a 20% approximation. Give or take. The reason people use it, and the reason it has the name Cowling, is that a guy called Thomas Cowling was looking at completely different oscillations in stars, the ones that go like this, okay? So they don't vary the density very much, they just shear, in which case, if you don't vary the density, you shouldn't vary the potential very much, and therefore this should be fine. So there are classes like that, I'm going to talk about those in a little while, okay? Where this is perfect. And that's true in general, okay? But even worse, we also do this in general relativity, okay? And then we take the Cowling approximation to mean that I can drop the perturbed metric, completely. Okay? Now this is hugely problematic because there are parts of the spatial metric that are linked to the gravitational potential. Okay? There are parts of the perturbed metric that are linked to the perturbed momentum. Okay? So by just dropping the whole metric, you could be losing important pieces. And so I'm just saying we do this, and you will find this all over research papers. Okay? And it's a trick. It could be valid. It might not be. And the more complicated, certainly in general relativity, one has to be very careful. Now, I'm not saying people shouldn't be doing this, using this as a step towards the next step, but one has to be aware that this is not, just because everyone does it doesn't mean it's the right thing to do. Okay? So it may not be legal. In this case, it is not legal, but I'm going to do it anyway because I'm in charge. Okay? That's why people that make the laws get away with breaking the laws all the time. Right? So now the only thing I need is a relationship between delta P and chi. So I'm going to get that by saying that the pressure is 0 at the surface. Always. In fact, this is the definition of the surface. If I find the 0 pressure of the star and I ride along with it, that's the surface. So that means that what I do is take this Lagrangian variation of the pressure I had, write it out as delta P. I have this displacement vector, the radial component, and then the radial derivative of the background pressure. That has to vanish at the surface, which we'll call big R. Okay? But I don't know what this guy is. Of course, it's related to the velocity field in the case of a non-rotating star. It is simply the case that delta V is the time derivative of this psi. Okay? We know that this guy was the gradient of a potential, so we just see straight up that I omega psi r is the radial derivative of that chi. But we know what this guy is, so I can work it out. It is just that A coefficient with an L from the derivative, R to the L minus 1, and then the spherical harmonic. So I can work it out. Okay? So now I know what sits here. I need to know what's sitting here. But the background is such that the pressure, so actually it should be a straight derivative, I guess. Here. Because it only depends on R, is balancing the gravitational potential. That's hydrostatic equilibrium. But I know what the gravitational potential is Gm over R. Take the derivative, there's a Gm over R squared, okay, which kills this I think I lost a sign. And then that just tells me I know, because this is a constant density sphere, I can work out what the mass, this is now the mass inside the radius R. It's not the total mass of the star yet, because this is local. So I work this out and see that the PDR just comes out as 4 pi G rho squared R over 3. Okay? And now I can plug all of this in here, and that gives me a relationship between the C and the A. Okay? equate that, but I solve it now for the omega. I get 1 power omega from here. I had one already over here. That gives me a squared. Just rewrite the thing, and that gives me an expression that says omega squared should be 4 pi g rho L by 3. And that's the end. Okay? So I did all that work just for this. But this is important, okay? It tells me a couple of things that will be very important both today. Okay? So I want to have a look at that. So this is the first thing we know is see that the frequency scales as the root of L, where L is the spherical harmonic. So if I go to higher harmonics, I get higher frequencies, right? With this scaling. I see that they also scales like square root of the density. So there should be a scaling like this. And then what you could do, which I'm not going to do because this is a real mess, I'm just going to tell you what the scaling is. If you take this assumption and you know what the step is at the surface in the delta rho, which is what you need to put into the quadrupole formula to calculate damping, the calculation was done by a guy called Steve Detweiler, one of my heroes, because he worked on pretty much all the problems I was interested in when I started as a PhD student. Sadly died fairly recently. But he did this calculation quite early on. It's a real mess, which is why I'm not doing it. But you can work out the quadrupole formula for this thing. And it's a mess simply because of this fact that you've assumed constant density, you got this step at the surface, and the whole secret is in that step. Okay? But if you work it out, you find that there's a damping time, let's call it TGW, which I'm not going to write down the numbers, it's about a fraction of a millisecond, so it's very short, but it goes like c squared r over gm to a power L plus 1, and then an r over c. Okay? And so there's a scaling here as well in M and R. Okay? So these are some basic statements. In particular, this will be useful shortly. Okay? But you would say, okay, look, this was a constant density sphere. It's got nothing to do with reality. Right? So we've just wasted 45 minutes of our lives. That's not a surprise to you. We've done it twice before this week, so that you know the pattern now. Okay? Waste a couple of hours in the morning, and then a couple of hours in the afternoon. No free time in this prison. Right? But you could ask the following question. What happens if I take a real neutron star equation of state? How many people in the room work on projects involving equations of state? Be honest. High up, come on. Okay, there you go. A handful, right? Or 10. So how many of you think that your equation of state is vastly different from all other equations of state? Oh, not much courage now. Okay, so you're all working on the same equation of state. Okay. The truth is this, okay? Equations of state have a wide variety of different approximations and different kinds of physics going in. But when you take a collection and you ask, is there a scaling like this in the results? The answer is pretty much yes, okay? And we know that because we've done it. In fact, here's a figure, two figures from a paper by myself and Kostas Kokotas from 20 years ago. Okay, on this problem. So these are outdated equations of state. Don't bother telling me that, oh yes, but we ruled out this one, this one. So you can take whatever collection you like, okay, and redo this. It's been done many times. And what you see is, here is the frequency of the F in kilohertz, from 1 up to 4. Different equations of state, you rename them whatever you want, some data. And you can see that there is a scaling with the density m over r cubed square rooted from here, there it is, okay? And I get that from this calculation, okay? So I expected this to be true, okay? If you go to the damping time, this is plotted a little bit differently, but here is that r to the 4th. If you take L to be 2 for the quadrupole, this is r to the 4th over m cubed. And here is that scaling, scaled to the compactness of the star for different reasons. That's just a way of bringing this collection close, okay? So what we've learned now, by doing this calculation, are some scaling relations seem to be fairly robust, okay? And so that's really great news. It means that if I detect something, I should not expect, for a given compactness, typical compactness of a neutron star, the result to stray much this kind of collection. Okay? That's good news. 1 plus. Now comes the bad news. Because there is this scaling relation, and pretty much all equations of state agree, I won't be able to tell you what equation of state it was. So I need more information, right? Or I need 2 pieces of information. So I could, for example, if I detect a frequency here and a damping time here, it's very unlikely that 2 equations of state agree on both, okay? So that's one way I could distinguish. Or I could look for other modes or other features, okay? So the bottom line is, it's not the fact that you have robust scaling relations might be great because you don't need to worry too much about what the variation is going to be, but it could be, it doesn't give you the whole picture. Okay, okay, so that's the first part. Now in the remaining half hour or so, I want to sketch more briefly what happens if I put in more physics. Okay? So obviously this was the simplest possibility. It's got very little to do with real stars. Apart from apparently, the lesson I learned is a sort of fairly realistic scaling. Okay, so the next thing I want to do is sketch how do we get, when we allow the density to vary, okay, how do we get sound waves and gravity waves in the star? How does that come about? Okay? So now let's allow density variations, but let's still not be rotating because that's too messy, okay? So then what happens is, just building everything we had before, you can go back to the Euler equations from the beginning and put things in, and you see, and still have this displacement vector, say. Then we got a second derivative of that displacement, that was the omega squared from before. We've got a, no, let's do it like this, equals. Yeah. We've got now density variations times the background pressure squared minus 1 over rho delta p minus grad I delta phi. So the equation changes to something like this. Maybe I should have put them all on the left, it doesn't matter. Okay. Well, that. And then we have where we have, as before, dt xi is delta v. And we get the continuity equation, which we can integrate because we've got a time derivative here, and we had one in in the delta rho. This is a problem we're going to look at tomorrow. Okay. So the problem now looks like this. Clearly, the trick from before is not going to work. The trick from before was based on saying, oh, this was a divergence of something, so I could write, it was irrotational and blah, blah, blah. This was a velocity potential, it's not, because it's not going to be an irrotational motion anymore, and this total gradient of this is not going to work because I got this piece. So this is not going to lead me to Laplace's equation. There's no way. It's going to be messier. In fact, I now need the equation of state. And even more than that, I don't need the equation of state. I need the equation of state when I perturb the system away from equilibrium. So I need the out of equilibrium equation of state, which doesn't have to be the same as the equilibrium equation of state. Okay? So this brings in all sorts of questions, like, is the system in chemical equilibrium? If not, are there reactions to bring it back? And then all this nasty stuff comes into play. But I'm going to kind of ignore that and follow what people typically do in this calculation, just to sketch it, okay? So what people typically do and I have to say that the more I look at this problem and work on it, the less I like this. I've got a different way of doing this now myself, but I'm going to do it this way because this is what we're going to find in textbooks, so that's the natural way to sort of do it now. What people typically do is they say, well, let me encode all my ignorance in something I'm going to call the adiabatic index associated with the perturbations. So I take all my ignorance and I put it in this box and I label it gamma 1. Okay, so gamma 1 holds all the secrets. To understand how gamma 1 is related to whatever physics you might want to look at is not easy, okay? But I just say I have this fluid element, is perturbed, so I look at delta P, Lagrangian perturbation, because I need, this is an equation of state statement, meaning sitting at a point and comparing things is not the right thing to do. I need to move with the box that has this fluid in it, right? This is proportional to, with some coefficient gamma 1, delta rho over rho. And then what people tend to do is to say, okay, let's call the sound speed. And if we're lucky at the end of the day, we're going to see why this is the sound speed. Let's just call it CS squared is P gamma 1 over rho, because then it says variations in pressure as we vary density is this sound speed. That's what we've written down here. So in some sense, that's what we mean. By sound is changes in pressure and density moving across this room, propagating mostly nonsense. Okay. And then what we need to know is, for example, that delta rho is the Eulerian delta rho plus the psi, I, something like this, okay? So now you have two options, okay? We put in Lagrangian variations here, because it's a natural way to connect with the equation of state. But I put in Eulerian variations here, because that way I was allowed to commute these two, the derivative and the perturbation. So I have to make a choice. I have to either stick to Eulerian, which allows me to use this equation, or I need to translate this to Lagrangian. or I need to translate this to Eulerian. Right? So that's what I'm going to do today. Tomorrow we're going to look at the other option. Okay? So if we do this, we can write down what happens to this delta P. Well, there's going to be a relationship between delta P's and so on that obviously has exactly these coefficients. So the first term is easy. It's going to be P gamma 1 over rho, that's sound speed, delta rho. And then I will have these pieces, one for the pressure and one for the density. Okay? So there's going to be xi dotted into something. And that something is going to be, first, the same thing again, P gamma 1 over rho, but now the gradient of the rho background density, and then minus the gradient in the background. And now, this is too much writing for an old man. So I'm going to give this guy a name. I'm going to pull out the P gamma 1 and then call the rest a vector A. So I'm just going to write this as P gamma. And write it like this, delta rho over rho plus psi times some vector A. This is defined by whatever that expression is. And then what I can do, now I can take this is what I'm not going to do. Okay? Take all this, plug in this expression for delta P into this, or write an expression for delta rho and plug it into this. It doesn't matter to me which choice you make. Right? It's going to be a horrendous equation. And then probably maybe it's best to work with delta rho. Keep delta rho because you got it down here. Right? And then try to stare at this problem. Break this equation into, say, a radial piece and a horizontal piece, where you get some pieces of those spherical harmonics. Mess. Okay? I'm going to skip to the chase in a sec. But before we do that, just look at what this says. Okay? And let's look at this guy here. Because this is the only difference, right? This would be very simple if I just had this term. So when does that happen? Well, that happens when variations in the background are described by the same relation as the perturbations, right? So if this adiabatic index here is the same as the relationship that you have in the background equation of state, then this term goes, right? So this only encodes things like when the perturbed fluid element is not in equilibrium with its surroundings. If it's always in equilibrium with its surroundings, then this term is gone. Okay? So that tells us what this term, this extra force is. It's called a buoyancy. Which is a great word to spell. Okay, so next, do the usual. So you expand in spherical harmonics and you work a bit. It's not messy, but you need to reduce this into one single thing. And then you assume, for the purposes of right now, I'm not going to calculate the modes. I'm going to look at the local approximation, just what happens locally. I'm going to assume that we got the e to the I omega t from before, but also a kr, some wavelengths and some radial piece. So that is an assumption allows me to, whenever I've got radial derivatives, just drop them, okay? So I'm never integrating this. It's called the plane wave assumption. So what I'm doing is I'm not calculating the modes, I'm just looking locally what happens, how do waves propagate locally, okay? And what happens at the end is, after the work, I get a dispersion relation that says that the wave number k squared is 1 over that c squared that I defined times omega squared, omega being this angular frequency again, and n squared, whatever that is, minus omega squared, and an LL squared, whatever that is, minus omega squared. So now I introduced many symbols just to write things down, but here we have the LL squared is just this LL plus 1 that you will recognize from before. So this comes from the spherical harmonics angular derivatives, the sound speed over r squared, and the n squared is, n itself is minus local gravitational acceleration. So this is just the local gravitational potential, if you like, times that A that I put in here, scalar version of this, okay, so magnitude of that. This guy has a name, but half the name is Finnish, and so I'm not going to give it to you, because I know that you will never be able to pronounce it. I've never met a person other than a Finnish person that can pronounce this name. Okay, so let's skip it. So this is a fast-forward sketch, right? I skipped all the steps. But I just wanted to get to here, because this is important, okay? We can learn a lot from this expression. First, we've seen that in this piece here, where it says work, the person that did the work managed to massage things in such a way that this answer factorized very nicely into two pieces, okay? I have to tell you there are some tricks involved in getting it exactly to that form, okay? No cheating, but some tricks with integrating factors and new variables and blah, 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 which is why I'm not doing it on the board. It would take too long. But when factories is like this, you can see that, okay, I know first of all that this guy is obviously positive, because he's k squared, k is in, right? That means that whatever is sitting here has to be positive. Now what does that mean? Well, whatever these guys are, this is positive. So this guy, if this guy is bigger than this guy, then this is positive. Then the frequency must also be less than this guy, right? And if this is negative, then that also has to be negative. So the bottom line is I learned that either the frequency has to be above the LL curve. LL is this guy, it involves a sound speed, and it scales with the radius in a certain way, right? So it depends on how this depends on the radius as well. So either have to be above these, below these. Okay? And so that tells me that I can only have waves of these kinds in regions where I'm above both or below both. Okay, so now I need to know which one is the biggest. Okay, so typically, I'm going to draw a little diagram. Typically means Nils just made this up. Okay, but typically, this is R. You get something like this. This guy depends on the composition of the star. It goes something like this. This guy has a 1 over r piece in it, so if it's roughly constant sound speed, which is not true, then it will go something like this. Okay? And now what did we learn? We have to be above both curves, below both curves. Okay? Up here, have sound waves that look pretty much like, you can basically see it here. If we're above both of these, and this one is much bigger than this one, then this frequency that you get out of this just goes like LL. That's essentially just saying, let's take the wave number to be small, this is a root. Okay? If we're below, then this is small, you can convince yourself that this is a root, so the frequency is roughly this. Okay? And so here we've got P modes, and here we've got G modes. Okay. So just to show you, here is a propagation diagram like this from a recent paper by Andrea Passamonti, where we looked at not just what happens if you got neutrons, protons, electrons, but also also muons in the composition. And so what happens here is, you see the graph I drew, LL squared, or it's called LB squared, here goes down like this, N squared goes down like this, that's what I drew, and then we've got a change in composition when the muons come in, and suddenly there's a lot of muons, so this gradient in the composition that leads to this N thing kicks in, and you get an extra bump here, which means you've got another region where you can have these gravity G modes. Okay? So you see diagrams like this all the time, and it helps us understand where do these modes possibly live in the star. I haven't calculated the modes, I've just given you a back of the envelope of what the frequencies could be, and perhaps given you an idea of what is the physics that goes in. Okay? And actually, this is a very topical thing, because the tidal problem that you talked about last week with Tanja, I don't know if she mentioned this, but some of us discussed this yesterday, there is a thing that's hotly debated right now, because there's a sequence of papers out of the MIT group that suggests that the tide that you worked out that leads to the love number may be coupled to the one P mode and one G mode. So there's a triplet of the tide, a P mode and a G mode that becomes strongly unstable and grows and completely destroys the in-spiral signal that is assumed for LIGO, which would be a disaster, because it would mean that all the search templates for binary in-spiral would be wrong. And of course we can say that today because LIGO hasn't seen any neutron star in-spirals. If LIGO saw a single neutron star in spiral and detected it with the usual tidal templates and so on, this story would be over. But right now, this is a very topical question. And it's a topical question for two reasons. One is the one I just described. It's an important problem, right? If this is true, we need to understand what the answer is. Otherwise, you know, we might be stuffed when it comes to detecting these things. There is another aspect, which is there is no one on the planet outside the people at MIT that are doing this calculation to understand what is going on. And I can say that because I'm working on this problem, and I have no idea what this mechanism is. It defies all logic as we understand it. People have worked on couplings like this for other problems, but this is different somehow. And we don't understand it. Well, I don't understand it. And that's a problem for me. But it's also a problem for everybody else, because I go around, people know I'm working on this a little bit. So wherever I go, people say to me, have you solved it? What is the answer? How do you? And then they say things like, oh, I'm not going to talk about this because Nils will explain it to you. And I said, but I don't understand it. So everyone comes to me and says, oh, how does it work? I say, I don't know. Go away. But they, okay.
Even this only affected the tidal information part, not the point particle.
I think that's, so I think in reality, it's a bit overblown, right? I think in reality what would happen is you would find the signal, but the parameter extraction would be completely messed up, right? That's what I think. But it's at the moment, you know, it started off with saying there is this instability between the P and the G modes. Okay, fine. Which one? The one I just raised? Okay, so the answer is no. We can talk about it later. But I mean, it's a very strange thing because when things couple, things usually couple because of a resonance. Okay. In this case, the static tide, the love number kind of deformation thing, doesn't have any oscillations to it. There's nothing that can resonantly couple to anything. So this is a non-resonant coupling suggested, and it's therefore with some arguments that some coefficient that in the coupling becomes very, very large. It's a logic I don't understand, as I said, so I shouldn't be talking about it. But basically what happens is you have some coefficient, let's call it kappa, that goes roughly like the frequency of the P mode over the frequency of the G mode. Something like this. And then the story, as I understand it, goes like, well, I can make this G mode below here very small, and I can make the P mode above there very large, and so I just let this one become very large and this one very small, and the kappa becomes huge. And somehow that's it. But there are some other bits here in the fine print that I don't understand. Okay, okay, so I've given myself.
How the love number? Because when you calculate the love number, you assume that it's static. So I don't see how.
No, it doesn't. I know, but I don't understand it. I've just said that several times.
You agree with me, or?
I agree with you. I agree. Whatever people say, I agree, because I don't know. Okay, I've given myself 10 minutes to talk about my favorite problem on this planet. So you can basically cancel Thomas's lecture now. But it's going to be quick, okay? So I want to sketch just very quickly a result that's going to be important for us tomorrow. And then in the, I think in the tutorial for tomorrow, today we're going to focus on the F mode, essentially, and understanding a bit more on that. Tomorrow I'm going to ask you to fill in some of the blanks that I wasn't planning on doing now anyway, in how this calculation goes. And what we're going to look at is a set of modes called the R modes. Basically, the story goes a bit like this. Now, if we put in rotation and we work in the rotating frame, then we get an extra piece to order omega, so leading order in rotation. We get an extra piece that looks a bit like this, the cross product between the rotation and the velocity field, and then we have the other stuff from before, delta rho over rho squared, grad IP, downstairs, yes, minus grad I delta rho plus grad I delta phi, and I got some sign wrong somewhere, probably here, something like that. I'm not going to write down anything else, I'm just going to look at this, okay? So this is the Coriolis force. Okay. the continuity equation doesn't change. So what we did before, it's worth asking, we wrote down a vector for the velocity field. We wrote down something that had, so think of it as a vector. We basically expanded in spherical harmonics, and we had a radial piece, let's call it W, say, times the radial direction. Oh, sorry, spherical harmonics as well. So L, let's put an L there. And if you look at the solutions I wrote down for the F mode, the other piece that we had was some function that was linked to this, let's call it V, that was linked to the gradient of the spherical harmonics. Right? So this gives us the F mode in general, or the P modes, or the G modes, all of them. Okay? They all have this structure. The velocity field looks a bit like this in another piece. These two are obviously linked. But this is not the complete basis in 3D, right? There is another direction, okay? So you could imagine saying, well, what is that direction? Well, one way of doing it is to say, let's just do this. I have two vectors. I can build the third one by cross product between the two. So why are there no modes like this? Why was there not a contribution like this? Well, there's a reason. This would be involving shear like this. Okay? But a fluid cannot sustain shear stresses. So therefore, in a fluid, this can't happen. But if the matter was elastic, like in the crust, you could have this. And in fact, those crustal oscillations I talked about for magnetars are exactly of this kind. And if it rotates, you see we've got a cross product here that essentially will bring that sector back into play. Okay? So now in general in rotation, for rotating stars, this problem is really messy, okay? If you think anything I've said so far this week is messy, this is where we reach the peak of messiness, okay? Because if you rotate, if this guy is now available for action, they can also couple. So as you write down different orders in rotation, say slow rotation approximation from non-rotating to slowly rotating and so on, you get couplings between all of these, and those couplings don't have to rotate. So you have to include not just one spherical harmonic, whole sequence, and ask, does this ever converge? Please make it so. Okay? So that's not the problem I want to do. I want to do a slightly different problem. I want to ask, what if, and you can show this rigorously, what if delta rho, delta p, delta phi are 0? Is it possible to find a solution to the fluid equation such that these are all irrelevant? Okay? Now basically, from the continuity equation we had before, you know that now removes the time-dependent part. We just have a divergence of something. Okay? You can argue that that is also going to disappear and become irrelevant, and I would only be left with this part. Okay? Essentially, what we're left with is the vorticity of the flow. So this will be a pure vortex flow, right? And if you go through the steps, which I'll guide you through tomorrow in the tutorial, there is a single mode for each L equal to M. That's important. A single mode that has this UL non-zero. Just one. Very special. Okay? And the frequency is simple. Has a 2 omega from the Coriolis force divided by this L times L plus 1 that we now know and love. We know that M and L are in fact the same. So this is just 2 omega over M plus 1. So if you put in M equals to 2, for the quadrupole this is 2/3 of omega. So that's in the rotating frame. It's in the rotating frame because if I'm in the inertial frame, I don't pick up this piece, right? That sits now in the convective derivative. But in the rotating frame, I get this. Now if I translate this to the inertial frame, then what happens is I have to subtract from this an M omega. Right? And that means that I have then sigma inertial is sigma I, sigma rotational minus, depending on your conventions. So that means I need to subtract for the quadrupole 2 omega from this. That means suddenly I have the omega I is minus 4/3 omega. Okay. So there's a difference in sign here. We should keep that in mind for tomorrow. But let's just close with one thing that will explain a little bit what this sign is telling us. Because we've got a dazzling 1 minute. Okay? And we can do that by sketching something called the pattern speed. So that is basically saying how does this mode oscillation move on the star? Okay? And the way you do that is just saying in general, you have those like the e to the I m phi from the spherical harmonic, which always decouples in a Fourier series, like this, plus my frequency. So I have a phase up here, right? So now I can say, well, constant phase says that m phi plus omega t is constant. But I can take a derivative of that to say that d phi by dt becomes minus omega over m. And then I can give it a name, sigma p. Okay? So this is called the pattern speed. Okay? And it tells us how this phase moves with respect to the star. Now if we go back here, we're saying, what have we learned? Well, we learned that this guy has a minus sign here, there's a minus sign there. So this guy, in fact, moves forward, right, in the inertial frame, but it moves backwards in the rotating frame. Okay? And just stealing a couple of seconds of your lives. Remember, we learned that for the F mode, it's scaled with m, like this. If we take L equals to m, right? So what happens to the pattern speed? Well, this is now positive, but there are two of them because I've got the square root like this. And let's just take the one with the plus sign, okay? What happens to this? Well, what happens to this is that the frequency goes like root m. But then when I subtract to go to the inertial frame from the rotating, this is going to be a rotating frame result essentially. I've got an m. And so this is going to win over this scaling at some point, which means that an F mode that starts out going forwards could end up going backwards at some rotation rate. Okay? So this backwards forwards thing is going to be the crucial point tomorrow when we start talking about gravitational waves and instabilities. Because that's essentially the criterion we're going to define as onset of instability. But for now, I'm more than done. Thank you.